Okay, so hello from my side as well. So my name is Vincent. I'm a PhD student at ETH Zurich. And what I want to present today is a project about letting users create user interfaces in any shape they want it to be, but still functioning interfaces to make them, allow them to do anything they basically want in terms of shapes and functionality. So the idea behind this project is that many of our user interfaces we have nowadays are graphical user interfaces. And they undoubtedly have many, many advantages. For example, that on the same display you can basically show infinitely many interfaces at different times. So you can use the same space. And you can basically also update them through software and so on. However, all the interface is locked away in the virtual world. So it's not possible for a user to reconfigure it easily, to touch the elements, to change things or to change the shape according to what they might think might be the best interface for themselves. So what we imagine is something like in this video where we're trying to control this presentation as a toy example now, and the idea would be to just be able to cut out your interface in whatever shape you want it to be. For example, this user might want some arrows to start it and then to switch the slides. And then after implementing some program logic, being able to use this directly in an actually working prototype. So not being like any fake system. And the initial idea we had was that, or assumption, is that all the users would probably, or hopefully, use very similar elements to control the interfaces. So there would be pluses and minuses to increase or decrease values, or arrows to change directions and so on, or some kind of track bars. And the idea was that we would then be able to automatically detect these interfaces and assign functionality to them. For example, that when you move this ball inside these two rectangles, this would act as a track bar. So to test this, we asked 20 participants to create such interfaces now without direct functionality in the beginning. Imagining, for example, they were in one of these 4 scenarios, for example, in the office, and they should create an interface to, for example, control the blinds, control the lights, and so on. A movie remote control, so you need like play, pause, rewinding functionality, imagine a remote control. A drone, so you need spatial commands, or a car where you would like change driving modes or the temperature. And for some participants, this was also, our assumption held, so many of them kind of made sense from an outside perspective. So for example, here you see in the office scenario, I hope you can see that there's some like slider-like structures, or for, can you see my mouse maybe? No. So you see that there's like a knob for the temperature, for example, or arrows for the blinds. And however, on the other hand, there were also some users who created things like this for the same scenario. So for example, here, everything to the user himself, everything made complete sense. So we also checked that everything of the functionality was actually implemented in this interface. So he just said, oh, I have different sliders here, this changes the blinds, and this the temperature, and so on. So our initial assumption did actually not hold. So there were not like a common set of actual shapes that described certain functionality in an interface. However, what we did find was that there were common abstract behaviors in these shapes that were commonly used. So for example, something like that, you can click an element as a button and it would act as a button, even though the shape might be completely different. So it might be a rectangle or any other arbitrary shape the users might create. So what we did is we went through all these interfaces the users created and tried to find these abstract behaviors, and in total we found 25 of them, which we call a touch-it. So a touch-it is like an abstract behavior independent of the shape this interaction element actually has. So for example, very commonly there's, for example, buttons, so elements you can click. Just to tell you, so these are just instances of these touches. So these are the pictures show examples. They don't have to look like this in the case the users created them, but they exhibit this behavior. Or there's positional hold buttons, basically where it depends on the region you click on your shape. Then you have sliders where you slide your finger across an element and this will change a value. Or you have sliders where you have two elements in relative position, so you basically slide with another element relative to another one. And some information was encoded directly by the hand very infrequently, and then we have two special ones. The first one, which we call containment, which is basically if an element is contained within another, and existence, which is difficult to show in an image because it basically means you encode information by the presence or absence of an object. So, for example, if a square is on the table, it should turn on the light. If I take it off, it should turn it off. And what we then did is went through all these interfaces and counted the number of instances for each of these abstract behaviors. And you can see here there's a quite long tail. In the front you have the most common ones, the buttons. Hold buttons is something that, for example, can sense a long press. And then there's many sliders and different types of trackbars. And what we did is we decided to implement the first 14 of these, covering having a high coverage across all the instances, with one exception, that is existence, because it's very, very difficult to track a paper element. If you take it off the table, imagine you take a red square off the table, put a different red square on the table of the same shape, you have no idea if it was actually exactly the same square or a different one. So existence very difficult to track. But even without this, we reached 92% of all the instances, of the actual instances in our first user study. So just to go through, now we want to track these elements, of course, because we actually want to be able to assign this functionality and be able to use them in actual applications. So just to walk you very briefly through the implementation. So we track the elements on the table. We imagine they're on a surface, on a single colored surface, such as a table, and we have a single camera as the sensor, so it's a depth camera, to track these elements. And what we do, we get two streams, the depth stream and the RGB stream, and we use the depth stream to track the hand and the fingers, because we assume that the hand is the only 3D element, let's say, inside this image, and we use the color image to track the shapes. And the first thing we do is use a convexity defects algorithm to detect the hand and the fingertip. In our case, in this implementation, it's a single touch interface, so we accurately locate a single fingertip, and then what we do afterwards, in the region of this fingertip, we run an optical flow algorithm which basically tracks certain feature points in this finger region, and which does not only make it possible to track the finger, but also compute the transformation between two frames of the finger, which also gives us the rotation the finger undergoes over time. So imagine you touch a shape, and then you rotate your finger, and we can calculate this rotation through this optical flow feature points, which is important because if you imagine you rotate a round shape, it's very difficult to track that from the shape itself because it's round, but through the finger we can get some additional information on this rotation. And it's important because many of the touches of the app behaviors incorporate some kind of rotation that needs to be calculated. And for the shapes, we have simply a simple detection on the table, assuming that the shapes have a different color than the table, which is quite easy. We, of course, cut out the region of the hand. And then the important part, of course, is manipulation tracking. So we figure out as soon as the user touches the table, which we can tell because we have a depth map and we know where the fingertip is, we can track what is actually happening to the shape from that shape plus this information we get from the finger. And then we propagate this information in the network via HTTP. So basically then you could grab this information in any application you have. So after knowing this, how this brief basically works, just to show you how a user would now actually implement such an interface. So after cutting out the shapes, he would then have to assign these touches. So this is the most important step. You have to assign this behavior. So for example, and we implement this in the same interface, like in the sense that you can touch the table and then do these selections through a menu. So actually you only need a single additional screen to do this configuration. And here, for example, you see he chooses an R touch-it, which means rotation, so he assigns this rotation to this square. So now this square can be rotated, but as soon as it's rotated, it will also propagate this information in the network. And what he's doing here is creating a sliding touch-it. So basically he's telling the system, okay, this is a slider, the blue triangle is the reference, and now I'm showing you what the maximum value range is, so what the extent of these values are. And now the system knows, okay, this is a slider relative to this blue triangle with these value bounds. And as you can see, there's also no limit to the number of touch-its you can apply to a single instance of a shape, because of course it can be a button, but it can also be rotated, and the single thing that will happen is if you click it, it will say, oh, I was clicked at this time step. If you rotate it or click it at the same time, it will just propagate both of these kinds of information. And the last thing you need to do in sense of configuring this interface is assigning what we call an action tag. It's basically simply an ID, because your application will need to know which shape did this actually come from, because you might have several touch-its which have the same functionality, so you just need to know, oh, this came from the touch-it or from the shape which now has the name rover. And now that you configured your interface, this will actually propagate all this information, and now the last thing remaining to do is implementing your program logic. And of course, you could do this in any framework you wanted to. And what we use here for our second user study is a framework called Node-RED. It's basically a programming flow, which easily lets you connect nodes into flows, which basically implement a program. Of course, for very inexperienced users, this might not be so useful. However, you could also, of course, pre-implement a lot of this logic. So, for example, have a program that opens the blinds, and then you just have to do a connection. So this touch-it with this value range opens and closes the blinds. And what we then did is actually have users create interfaces from scratch, including this programming logic. So we got 6 participants from computer science, so to make sure that they could implement this last part of this programming logic, because we did it really from scratch. So it also required, if you want to have very complex interfaces, to implement some parts in JavaScript. And here you can see 3 tasks, so they also serve as a demo here. So basically you can control, you should be able to control a little toy rover through some interface. Again, these are only example interfaces. This slide presentation I showed you in the beginning, and also a music player application. So in the top rectangle, you can see that it's changing the volume, changing the songs, the tracks that are played. And but this could look different for every user. And why we had so few participants actually is that we actually spent quite a lot of time with each participant. So on average, a participant spent over 2.5 hours or over 2 hours to do all the 3 tasks. However, this might seem very long. However, it strongly decreased from the first task to the second task by over a half. And the fastest interface, for example, was created in 11 minutes, including all this programming logic. The reason they actually stayed so long is that we deliberately did not restrict them in the time they had to create these interfaces. So we didn't tell them do it as fast as possible and finish immediately once you have one, because we wanted to see how they actually interact and use this kind of prototyping system. And what actually happened was that people deliberately stayed extra long to try out new interfaces. So we had one participant who in total stayed 5 hours, even though he had finished like several times this kind of rover interface, for example. He continued to do new ones, try out new things. And this is also what participants said, that it was really fun trying out new things, because you can immediately see what happens when you use this interface and see the actions you can implement. And we believe this is one of the strongest advantages, is that you can actually really spur creativity, because you close this gap between actually ideation of creating such an interface and the actual implementation, so you can use it immediately. We also had them fill out a user experience questionnaire, which is a questionnaire to evaluate user experience of products, which goes from values from -3 to 3. And just some key results are, for example, you can see very high perspicuity, which means that it was easy to learn. Participants also told us, especially because you don't have to learn so much, because you're doing exactly what you wanted to, and it was really stimulating and helped them to be creative. So just to finish, you might think, what do I actually need this for? So one obvious reason, and what you've seen now mostly, is of course rapid prototyping, because you can close this gap between creating an interface and actually using it, and then iterate faster through your process. However, you might be also able to use this in kind of building automation. At least in the test phase where you construct your building and don't know the exact office layout, you might want to be able to test things. So you can just stick controls on the walls, and let's say the tracking range was bigger. And then instead of wiring everything in the walls in the beginning, you could just test out things, have buttons here, maybe change the configuration because you don't like it, and so on. The same accounts for workspaces and factories, where workers visit machines very infrequently maybe, and they're not used to these controls. So instead, maybe they bring their own controls with them, their own interface, which they take with them, back with them in the end. Or maybe potentially even disabled people, for example, visually impaired, could use this to build interfaces for themselves, built by themselves, because we assume they might know much better what they need than visual people who can see normally. And with that, I want to finish and hope you have some questions.
Thank you. So is there any question?
Oh, yeah.
Hi, Raimund Axfeld, Interactive Media Lab Dresden. Very nice presentation and interesting work. So I think it's really great prototyping method. Could you go back to the one slide, to the applications? To be honest, I did not fully understand like the potential. For example, for changing workspaces, you would need a huge tracking system to do that in space. I understood, and also for dynamically changing. For building automation. For building automation,
exactly.
You would need exactly. So this would be demanding, and also for changing workspaces. I'm not sure whether you really can change the interface of a machine. I mean, I have not seen a machine where you can easily do that. So maybe you can expand a little bit more on the actual usefulness of your approach, for which kind of applications it's useful.
So for the machine, of course, we imagine you can't change the API behind it, but so, for example, what often happens is that people have to inspect machines and look at different value ranges. So in that case, of course here for machines, the tracking area would not have to be so big because you're only tracking the interaction area. For the building automation, I clearly see, so this is definitely only the far future potential because the tracking range needs to be so big, and you need potentially have many cameras. And you also saw from our interface setup that at the moment this is not really possible because the camera had to be quite close to the interface. But we could imagine for the future that at least for a layout phase that you can simulate your wirings in your wall by such an interface. But we haven't tried this out yet, so it's true. We're not sure about this potential.
I would really think that building automation is probably not a very realistic use case, because I have never heard that once a building is built and nobody thought about how to put the wires beforehand.
Oh, actually, this happens often. So this actually,
really?
We checked. So this actually, also at ETH, this happens that people figured out, this wire is actually doing the wrong thing. This shouldn't have been in this place before, and now we have to change it. And actually, that it's not only. Well, this is not an application of ours, but it's not only actually where the interfaces are, but actually that they're wired incorrectly. So this actually does happen.
Okay.
Hi.
Yeah.
Lauren Thévin from LMU Munich. My question was about the possibility to prototype a kind of remote controller. And my question, I have then two questions related to the perception with the depth camera. Could we imagine to have like a paper remote controller in hand and to interact with a button with a second hand? And could we detect like pinch controller, for instance, for the cross controller? We could detect which arrow we are pinching. So it is clear?
Do you have an example for an interface? So what it's on your hand?
So, for instance, if you hold like a hard paper remote controller with different button on it, could you use a second hand to click or push the button on it, and then it is possible with the depth camera detection? Or could you just like hold different button in the air and press it and detect it by the pinch?
So for sure, it might be possible. In our concrete prototype, it would not be possible to hold it in your hand because we very accurately actually figure out the plane the interface is in, because the depth camera image is very noisy, so you have to have a very good baseline of what your plane actually is. So if you hold it, it will have a lot of variation over time. But it could be possible if you in the end figure out that this is your interface and you only track this part, it should be possible. For the second one, you have what was the case? You have a button in your hand, or you only have a single button. So also not in our current implementation, it's not possible, but if you accurately can track this button, it should be possible, Okay. Yeah. Oh, yeah.
Hi, Tim Dwyer, Monash University. Thank you for the talk. It was a nice talk, and I admire the technical aspects of this work quite a lot. But I worry a little bit when you talk about trying to close the gap between prototyping and implementation, and because I think part of the idea of paper prototyping is actually to enforce that gap and to free people from concerns about the specifics of the implementation and the technicalities of the system, and focus purely on creativity. And I wonder, do you have similar concerns, or how would you counter that query?
Okay, yeah, we didn't think about it like this. So this is like, let's say, maybe a philosophical argument we could have about that. What we saw is that, so it's true that in the end, you spend actually quite a significant amount of time of your prototyping experience, let's say, with actually implementation issues. Specifically in our case, what actually took them quite a lot of time was doing this programming logic in the end, like through this Node-RED interface. So there I can see a concern is that for a user, if you have a participant in your lab for a short amount of time, it might actually be still too tenuous to create these kind of full implementation interfaces. So there I would agree that just having them quickly create something from paper is much, much faster. From the thing that it actually stops you from actually being creative, so what we saw, at least in the user study, of course, were not so many people, was more or less the opposite, but people were getting more creative because they could actually see it working and wanted, and then they saw, this thing, they figured out quickly, this is possible with this interface, so I'll try something more challenging or with more complex items. So, yeah, I'm not so sure about that.
Thank you.
Thank you. So let's thank our speaker once again.